Hey guys, Andre from High Performance Academy here. Welcome along to another one of our webinars. Now today we're going to be looking at transient fuel tuning on the Haltech Elite 2500 ECU. This is one of those aspects that I know even a lot of professional tuners really struggle with, and getting your transient fuel tuning correct can be the difference between a car that drives nice and smooth just like a factory calibration and one that's barely drivable. So it's something you really do need to focus on getting right. We'll get into that shortly, but before we do so, just an update on what's been going on around HPA Labs over the last week. And if you joined us last week, you'll know that we didn't have a very successful weekend at the 1 hour endurance race that Ben and the team attended at Teardown Motorsport Park. Unfortunately, our 1UZFE let go in a fairly spectacular fashion. Now, I showed last week a couple of shots. We hadn't actually got the engine out of the car at that point, so it's a little bit limited on what we knew, and I'll just give you a bit of an update now. We haven't actually got the engine apart, but we've got it out of the car, and let's just say it's not looking too healthy. So I'll jump across to my laptop screen. This is the photo I showed last week, so this is actually shot underneath the headers with the engine still in the car, so it's a little bit hard to get too much perspective, but fair to say there's not a lot of good things happening in there. Nice to see that the conrod actually looks like it was still intact. The wrist pin obviously still through the connecting rod there. Getting the engine out, this is another view through that same hole, and normally when you can see the cylinder head looking like that, you know that you're not going to have a lot of parts left to reuse. At this point we are speculating, but it does look like the cause of the original failure is probably to do with the valve train. Possibly we've ended up with a valve contactor piston, possibly a valve has dropped. So you can see in this instance we've got a nasty bend in this particular valve. This one snapped the head clean off. This little guy here, I think we found him outside of the car. I'm not sure, but there he is anyway. Safe to assume that no amount of coarse valve grinding paste is going to get this little guy back into an operational form anytime in the near future. Now, actually don't know off the top of my head exactly what the specification of this engine was or what it is. I can't tell you what that valve is. I don't think it was the factory valve. It could quite possibly be a Supertech aftermarket valve, but again, got a little bit of digging to figure out. Essentially, for those who aren't aware, we inherited this car from a customer we were dealing with. We were doing the electronics and the tuning work on the car. He had the engine built by a local engine builder who deals with building these 1UZFE Toyota engines for the stock car market, where they run as a sealed engine in a specific class. So that's the valve. We've also got a couple of little mementos here that came outside of the engine. Probably a combination of what's left of piston, maybe some cylinder wall as well. Again, doesn't really matter, not particularly usable. And again, just to show some signs of how ugly this all got, when you pull the inlet off the throttle body there, and you can see some nasty pieces of aluminium shrapnel sitting up on the outside of the throttle plate, you know that things have gone catastrophically wrong. And you can see there the amount of shrapnel just inside of that throttle butterfly. So not particularly pleasant sight to come home to and find all of this carnage, but unfortunately that is motorsport, and if you are in motorsport for long enough, at some time you're going to have a failure of this magnitude. So there's the inlet manifold with the top of the plenum chamber removed, and again, just the sheer amount of destruction to get all of these parts up outside of number one cylinder, which is the one that let go, and sitting them up there in the top of the plenum is actually pretty spectacular. The downside of this, of course, is that when the engine let go at something like 8 to 8,200 RPM, by the time Ben actually managed to get the car stopped, the engine's obviously spun over a lot after the failure. That tends to distribute all of these parts through the other cylinders. So essentially, we're really not expecting any recoverable parts. Maybe the rocket covers might polish up, we don't know, but we'll see what goes on once we get a bit deeper into it. The other aspect here is inside of the plenum chamber. I actually managed to find a couple of pieces of ring from number one piston, so again, it is quite surprising just how bad these things can get at that sort of RPM when they Chernobyl. However, we're not going to let this get us down, and yesterday, this replacement donor engine turned up. Again, obviously, we're not going to have a lot to work with that existing 1U ZFE, so we chose to start with a fresh donor block. So this turned up from a local wrecking yard. So I just want to talk a little bit about the specification for this new engine and a bit of the planning that's going into it. So this really comes down to some of the considerations that a lot of enthusiasts will have to make, maybe some of you watching today, when it comes to planning out an engine, and some of the considerations that we're going through here, so you've got a better idea of what we're sort of thinking about and how we've gone about and approached it. So first of all, it's important to understand the race series that we run in, the South Island Endurance Series. The class that we're running in is 3.5 litre engines and above. So basically, once you're above 3.5 litres, other than GT3 cars and Porsches, which get separated off into their own class, it's a free-for-all. You could put whatever engine you want in it, forced induction, supercharged, doesn't matter, anything goes. So fair to say, when we are dealing with a 4 litre V8 that makes around about 450 horsepower flywheel on our dyno, we are significantly outclassed. There are a couple of competitors running at 700 horsepower GM LS7 V8s. We've got another competitor, we believe, joining the fray next year, running a 700 horsepower Toyota 2JZ turbo engine. We're not going to be able to get up to that level, and what we want to do is be a little bit mindful of the amount of time and effort and resources that we have to pour into this car. That straight away eliminated us from re-engineering the car for another engine, although we did go very briefly through a bit of a tangent when we had on offer the potential for a Judd 4 litre V8. That would have been great, particularly, probably in my opinion, one of the best sounding naturally aspirated V8s, but that didn't transpire, and realistically we probably didn't have the time available to get all of that work done. So what we want to do is basically maximize the capacity of the engine that we are dealing with here. Ideally, to be a little bit more class competitive next year, we want to be somewhere around about the 550, ideally maybe 600 flywheel horsepower, and that's a big stretch from the 450 we're at the moment. So of course, when it comes to naturally aspirated engines, there is no replacement for displacement. We want to get a little bit more capacity in there, so this is why we've actually started with our next donor engine being the 4.3 litre 3U ZFE. Now there is another big brother in that Toyota lineup as well, the 2U ZFE. It's a truck engine, and it really wasn't suitable for us, despite the fact it gets out to 4.7 litres. We go from a nice light alloy block to a cast iron block. Definitely bulletproof, but we're not sort of making the kind of power and cylinder pressure that we need a cast iron block. The other problem really is that 2U ZFE block weighs something like about another 35 or 40 kilograms, and we don't want that weight over the front axle line. So alloy block it was, 3U ZFE is the way we've gone. Now those blocks actually identical between the 1U and the 3U. The only difference there is in the bore diameter, and it's a factory sleeve in that block. Takes us from, off the top of my head, I think we're 87.5 millimeter on the 1UZ, takes us out to 91 millimeter with the 3UZ. For reference, the 2UZ, that cast iron truck block, is a 94 millimeter bore. So really the capacity all comes down to the bore. Actually, that's not quite right. There is a slight difference in stroke with the 2U crank. I'll come back to that. Keep your notepads out, because I know I'm chucking a lot of numbers around, but hopefully this is of interest to some of you going through this process anyway. So the 4.3, that's the one we've gone for. Now, of course, we would have the option to sleeve a 1UZ block. We could go bigger than 91 millimeter. We could go to 94 millimeter. The reason we don't want to do that is that sleeving at best is an expensive process, but at worst as well, it can actually fix one problem, which is bore strength and bore capacity, and create a whole new set of dramas with sleeves dropping and leaking head gaskets. And frankly, we don't want to be in that scenario, and what we do want is a situation where if we are unlucky enough to have another failure, we can easily replace this engine, rebuild it, get it up and running quickly with off-the-shelf parts from Toyota. So that's the sacrifice we're going with. We are going to be stuck at or about that 91 mil bore. We can actually go to a 20 thou or half mil oversize quite safely there. So that's going to get us out to somewhere around about obviously it's going to get us out to 4.3 litres with that stock stroke crankshaft. So we're looking at our options to go a little bit further. The first of them that I investigated was actually offset offset grinding the factory 1UZ crank. Now again, yes, we could get a billet crank made, hugely expensive, and again we're in that same scenario where we're starting to use custom parts where if we have a failure we're going to be sidelined for a long time while we get another crankshaft manufactured. I don't want to be in that scenario. So again, we've made the decision to stick with stock parts. So what we can do here is offset grind the big end. So basically we need to match this up to a different diameter big end journal for our connecting rod, and in stock form the 1UZ crankshaft is, I'm just checking my notes, 52 millimeters in outside diameter. Now a really common bearing size that is used in all manner of different engines is the Honda B series big end journal, so that takes you down to, I think off the top of my head, yeah, it's 45 millimeters. So what we can then do is essentially offset grind the big end of the 1UZ crank. That lets us offset it by 7 millimeters. What we need to consider is it's actually the center line we're moving, so it gives us another additional 3.5 millimeters, half that offset in terms of additional stroke. Again, hope you're paying attention here. We are getting to the end of this. That would get us out to 4.6 litres, which is definitely a healthy increase over the 4.3 3UZ. Great increase over our existing 4 litre capacity. However, speaking to the company that originally built this engine, they specialise in these engines. They've actually gone down the same path themselves and found that the 1UZ cranks don't take kindly to offset grinding and have failed. So we're sort of back at square one. At this stage, we're thinking we might just bite the bullet and stick to 4.3 litres. We can also use the 2UZ crankshaft. That takes the stroke from 82.5 to 84 millimeters. It's quite an expensive option for just another 1.5 millimeters of stroke though, and essentially all things being equal that gets us about a 90cc capacity increase. So if we can essentially get the same power per litre that we've got now and just increase our capacity, that 90cc's is basically worth about 10 horsepower. So it ends up being a pretty expensive 10 horsepower. That's where we're at the moment. Obviously, regardless what option we go with there, particularly if we go to the Honda big end bearing size and offset grind the crank, we're probably sidelining that, but either that would still require a custom connecting rod, but no huge deal there. The other aspect is that in stock in the form that these engines were built by the supplier, they are limited to 10:1 compression for the stock car class here in New Zealand. We obviously don't have any limitations. We do still want to run on pump gas. This is because in ethanol fuel, the additional fuel burn for endurance racing, it just isn't worth it, so we don't want to be doing additional pit stops. So we're probably going to be looking somewhere around about a 12.5:1 compression. That should be something that is manageable on the pump gas without us being highly knock limited. The other aspect is with the cylinder heads, we're going to be going to an oversized valve. Obviously we want to address why we've got this problem with the valve dropping or what's happened there in the first place. So that's something we need to get on top of. We definitely don't want a repeat of that. And we're also considering a switch from the plenum chamber with single drive-by-wire LS throttle body to a set of crossover ITBs running the drive-by-wire system. That remains to be seen if we go down that path. Hopefully if we do all of that, should free up airflow on the intake side, and hopefully we can get up around that 550 flywheel horsepower. We also don't want to sacrifice our revs at the moment. It's got a nice wide power band from about 6,500 up to about 8,800 RPM. In fact, we'd like to extend that up with the ability to rev that engine up to about 9. So there you go, some of the considerations that we've gone through. We certainly haven't finalised our decision yet on exactly what that specification will be, but we're hoping to get that squared away in the next couple of weeks so we can start getting some of these custom parts made. Obviously we want this engine back up and running and the car back up and running as quickly as we can. Alright, we'll move on. Let's head back across to my laptop screen, and this is an Instagram I put up a couple of days ago, and I just wanted to bring this up because it is relevant to our 3UZ, 1UZ discussion as well. This is a shot I took at PRI. This is of a naturally aspirated drag car, and what we can see here is that each of the headers has an individual cylinder Lambda sensor fitted to it. So we've got 2, 3, and the other one's hiding around the back. Now, I just want to talk about this because I think it's something that is often misunderstood or overlooked, in that when we tune engines, generally what we do is we have a single Lambda or wideband oxygen sensor fitted to the exhaust. Usually that's going to be in the collector where it's sampling all all cylinders. In this case, obviously, 4 cylinders on each side of a V8. Now that's all well and good, but the problem with that is that we are actually just seeing the average of the air-fuel ratio across all 4 cylinders. Now what that means is that we could easily have one cylinder that's a little bit rich, we could have another cylinder that's a little bit lean, a couple in the middle, and essentially the number that we see on our data logger or on our laptop is exactly where we want it to be. Now that's okay for most instances, particularly in low-powered street car engines. It's probably not going to be the end of the world if we've got one cylinder running just a little bit lean. As we start increasing the specific power levels, increasing the cylinder pressures and pushing the engine harder and harder though, the envelope that we're able to run the engine in safely starts to get a little bit narrower, and what we can now find is that one cylinder being a touch lean could actually result in a failure. So this is why individual cylinder Lambda sensors like this become a really powerful input. Traditionally this was done, particularly at the start of my career, we weren't seeing a lot of wideband controllers like this, and they were very expensive. So traditionally it was actually done with exhaust gas temperature sensors, one in each header. That gives us some data, but the problem is that while the air-fuel ratio will affect our exhaust gas temperature reading, it's also influenced by a number of other parameters, such as the coolant flow around the cylinder head, the ignition timing, and a range of other aspects. So EGT not necessarily a perfect indicator of our air-fuel ratio, will give us an idea though. Obviously if we're monitoring the Lambda directly, then we know exactly what the air-fuel ratio is. We can trim. Inside of the ECU there'll generally be individual cylinder trim tables, so we still tune the engine overall with a single fuel or VE table, but then we can account for any discrepancies on individual cylinders with a 3-dimensional trim table versus load and RPM. Now these sensors, while we can leave them in the exhaust header the whole time, generally and particularly on turbocharged engines this can be quite hard on the sensor, and you can end up experiencing a reduced sensor life. So quite often these will be used only for the dyno tuning, and then those O2 sensor bosses will be blanked off once the engine has actually been tuned and heads out on the street. Now also I've been talking a little bit lately about our RaceCraft sister project, and I want to just jump over to our RaceCraft Instagram account as well. If you guys aren't following at RaceCraft already, please make sure you do so. We're RaceCraft HQ, like High Performance Academy, but for those who want to optimize the performance of their race car. This was a short tech nugget that we shot while we were at World Time Attack Challenge last year, and we talk about what an adjustable brake bias is and what a pedal box is. So how exactly these work with dual master cylinders to enable us to vary the bias between the front axle and the rear axle braking. Really important, particularly more so for those without ABS, to allow the driver to adjust the bias forwards and backwards in order to optimize the braking performance. This is important as the fuel load in the car burns off and the weight distribution in the chassis changes. Also really important to optimize the setup between dry and wet as well. So if you want to learn a little bit more about how to make your race car go faster, also how to drive your race car quicker, then check out RaceCraft HQ's Instagram account. And lastly for today, I'll just head across to our YouTube channel, and this is our latest Tuesday release here. This is a video that we shot back in July when we at Mountune when we went to Goodwood Festival of Speed. And Mountune, well known for creating numerous different types of engine. Here we're talking to David about the development of their World Rallycross engines. And while these engines on face value aren't maybe the most powerful things in the world, they generally produce around about 600 horsepower. They are actually restricted, so this is why they only make 600 horsepower. They run a 45mm inlet restrictor. This restricts the airflow through the turbocharger, basically chokes it at high RPM. So while the high RPM power from these 2-litre engines isn't anything particularly spectacular, we see probably a lot of road cars now making more than this. What's easy to overlook is that at lower RPM they can run massive amounts of boost pressure, 3 bar plus, through these turbochargers, and these engines are seeing in the region of 850 newton meters of torque at low RPM, and it's really difficult to keep the engine together and keep it reliable under that sort of cylinder pressure. So we're talking talk to David about what exactly goes on in the development and how they overcome their head gasket sealing issues. You might be surprised, regardless of the different techniques with wheels, rings, gas-filled O-rings, etc., out on the market now that are commonplace in high-powered turbocharged drag engines. Mountune actually ended up finding that a very special type of MLS or multi-layer steel head gasket was the best solution for their purposes. Right, so head across, check that video out, make sure you subscribe, give us a thumbs up on that video if you like it. If you've got any questions, please ask those in the comments. I'll be happy to jump in there and help you out. Actually, I said lastly, but one more last, so that was our second to last. This is our actual last. We are running another one of our giveaways. It's just gone live recently, and this time we have partnered with the team at AIM Sports, and we're giving away one of their AIM SOLO2 DL lap timers / data loggers. This is a really powerful tool. We've been using this a little bit for some course development for our RaceCraft sister project. Probably one of the cheapest ways of getting you some really high quality data. Actually, if you win this prize, it doesn't get cheaper than this because it's absolutely free. The AIM SOLO2 DL is really easy to put from one car to the next. It comes with a roll cage mount, or either that or a suction cup mount. It is fully self-contained, so it includes a GPS, also includes a 3-axis G sensor, and will give you all of the data that you require, including being able to generate lap times, predictive lap times, and track maps after you've downloaded that data. Nice feature with the AIM Sport data package is that you can also download wirelessly, so there's no need for clumsy cables and climbing in and out of the car to get your data out of this unit. Now, the AIM Solo 2 comes in two models. There's the AIM Solo 2 and then the DL, which is the one that we're giving away. The DL adds the ability to integrate data from your ECU. It's compatible with the majority of common aftermarket ECUs, and a simple 2-wire CAN bus from your ECU to the AIM Solo 2 DL will get you all of that data. Really easy to configure. Choose your ECU type from a drop-down menu, and it's as simple as that. Also, via the OBD2 port, you can also gather data, some of the common data from most factory ECUs. So really powerful. While the GPS and G-force data on its own is a huge benefit to data analysis, being able to integrate that with aspects such as engine RPM, throttle position, wheel speeds, etc., really does open up your capability to analyze that data in more detail. Now, you can head across. I'll get the guys to put a link in the chat that you can follow if you want to get yourself into that draw. We are running that for another 16 days, I think, at the moment. That'll also come with the RaceCraft wheel alignment fundamentals course, just helping you get a little bit more knowledge about how to set up your race car. And when you enter into that draw as well, there are a range of other little tasks you can do to get yourself more entries into the draw. So 16 days to go, absolutely free to get your name in that draw. It's a great prize package worth over $800 US. So head on over there and get your name in. Alright team, thanks for watching today. Give us a few moments and we'll get started with today's webinar. If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.